Okay, so we have two sessions to go, or two sessions. The first is some announcements by Alejandra, and I think by Alejandra, and I think David also has a few things to say, and then we'll transition to the let's say the experiment of having the panel discussions between the chairs. So maybe if I can call Alejandra up. Oh, you're giving the announcements. Oh, okay. You can get the announcement slides.
No, I'm just going to talk about strings committee and then bring.
Sure.
She'll come.
Oh, okay.
Just inverse order.
Okay.
Okay, so I'm here to do two things. One is try to moderate this experimental closing session, but the other thing is to report to you from the Strings Planning Committee. So, Strings Planning Committee consists of a bunch of us plus a rotating group of former organizers of strings conferences. We met yesterday to discuss the current situation, or more precisely, the members of the committee who happen to be here, which is actually most of them. Hirosi Ooguri, Edward Witten, Igor Klebanov, Rob Meyer, Eva Silverstein, Sasha Zebedovsky, Stefan Friedenbergen, and we invited as well Ahmed to join us since he just organized this incredible conference. So I can't help thanking him again, even though we've thanked him over and over, but he deserves it. It's unfortunately a major task to organize such a conference, especially in Abu Dhabi, which is in a very new university, which hasn't done anything like this before, so it really is novel. Of course, he had the help of an incredible committee of some of us who helped him plan the program, which I think was extraordinarily good, including many very interesting innovations compared to past conferences. There was enormous emphasis on the contributions of young people, which was absolutely wonderful. There were various experiments, some of which were very successful. In fact, the closing session is an experiment. We'll see how successful it is. And that's part of, I think, the great thing about these conferences is that nothing is laid down. We continue to, different organizers continue to experiment with different formats and different ways of running the conference, which is great. We're completely flexible. So let me report on the current situation of these conferences and where we are after our discussions over the last year, or half a year really, since the last conference. By the way, isn't it remarkable that this conference is only half a year later than the wonderful conference we've had in CERN, and yet there's so much exciting new stuff in just one half a year. It suggests that perhaps one needs to run this conference every half a year. Unfortunately, as I'm coming to, where the plan, the vision, sort of coming back to normal summer conferences, was that the next Strings conference would be in the summer of 2026. And instead of having a conference half a year from now, there might not be any conference next year. That's the current situation. So normally at these conferences, at the end, before the vision talk, or in this case, the panels, the organizers of the following conference get up and say, we're going to have a conference a year from now on X, Y, and Z, and look on the website, et cetera, we welcome you to Z, Y, or X. That we cannot do at this point. We don't have anyone, any group, who has currently committed to holding a conference in the summer of 2026. Now, that's a year and a half from now, so it's not a tragedy. And in my opinion, it would be a tragedy if we actually go through next year without having one of these conferences. So the strings, so-called strings, which is perhaps not the best name, since this conference encompasses not just string theory, some might argue that's everything, but also just about all areas of fundamental physics. And it is extremely unusual if you think about it and compare it to other conferences, and there are many other conferences. But what is unique about this one is that it brings all of us, and all of us is a very diverse and enormous community together. Typically, with only one exception that I know of, we have exciting parallel sessions with reviews of important areas in the developments which enable us to remain as a community with common interests and common knowledge. And that is extremely important for the kind of science we do, because areas which hold their own little workshops and small conferences throughout the years and don't know much about the other groups, this really is the opportunity for them to learn about things which might to them seem so far away and unimportant and boring. And the talks in this conference, the review talks and the contributions are so well done that I'm sure one could argue that it's extremely productive in how rapidly we move forward in this difficult field. It really would be a great tragedy that this conference dies or stops, and we might be faced with that. It's also a very unusual fact that, this conference is, over the last 35, 40, years, has been going strong. There have always been groups that are volunteered and went to an enormous effort to run such conferences. It's completely comes from the bottom up. There's no organization that runs it. There's no money. There's no group that can finance it. So part of the trouble and the obstacle is that groups have to raise their own funds. Many of us can help with that, but that's a barrier and a problem. But it really is a sign of the vitality and strength of our field in general, that it has survived so long, and in fact, in my opinion, the quality continues to improve. So I can't tell you where the next conference will be. What I can tell you is that our committee is concerned about it and working on it, and we're confident that there exists a solution. We will find the solution, and within hopefully the next half a year, because one really needs to know a year ahead of time, we will find a solution. There are some ideas. We can't really discuss them at this point. There are some real possibilities, but nothing is definite yet. But within a half a year or so, we'll be able to inform you all about where the next Strings Conference will be, where and when the next String Conference will be. Okay, so the plan now is we're going to have an announcement from Alejandra Castro about the decision that came about in the American Physical Society about the postdoc deadline, which is an issue that came up last year at the Strings Conference. We discussed it, voted, I think, and Alejandra and others have been involved with the APS in coming to a consensus that hopefully will set a standard that we'll all be willing to accept and bring some uniformity and rationality into the process.
So, this will be quick. We'll talk about the sitter. No. Yeah, as David was saying, and I hope everyone knows, I hope this is not shocking news, but we've been trying to figure out what the new postdoc deadline accord would be. So if you have not been informed for any reason, or if you don't know what's going on, we have a website, and you can read all about what we have been doing in this past month. So here's just a quick review. It started in June. We had surveys, we had town halls, we wrote drafts of the report of the recommendation we were going to do. We asked for feedback on that draft. I think we covered all of our corners. We heard as many voices as we could. And the outcome of all of this beautiful process is that the recommendation that we will put forward to the APS is that the deadline should be January 31st. Is that clear? Because I don't want to do this again, just in case. Okay, so it should start in 2026. And the thing that you will notice that will happen next, I don't know the details yet because we're at the stage that we'll submit this recommendation to the APS. But what you should be looking forward to is the implementation of it. And as I said last year at Strings, I hope we're not children and we all behave like grown-ups and stick to this. Is that clear? Okay, thank you. Could you hear me? Was it clear? Yes? Okay, January 31st, we're done. Thank you.
Hello? So the procedure that has been decided by the committee for the closing session is we're going to have 3 panel discussions. The panel members are the chairs of the sessions during the conference, and they each we'll start out with a 1-minute question, statement, comment, prediction, whatever they want, 1 minute, and then we'll try to have a discussion between them. They will respond to other people's interventions or raise new issues. We're not going to have any questions or answers from the audience. So that's the way we have been instructed to behave. It's an experiment. We'll see how it works. I think the panel members all know which panel they're in, all have prepared something, and should take their seats. So let's start with the first panel, Jan de Boer, I think Dan, Rob, Juan, everyone is here. And, okay. Okay, so I'm just going to make sure you don't go overboard. And let's start with Rob and move around the circle, semicircle. Rob.
Okay, this is an interesting experiment, but I'm game. My question, well, I had a whole bunch of questions, but I was inspired by the KITP, and they're all what is questions. And so my question is, what is space-time? And so what do I mean there? Well, usually when we're talking about quantum gravity these days, we're inspired by holography, and we spend a lot of time understanding the boundary theory where we're not really doing quantum gravity. And that's a shortcut to understand interesting phenomena. And I'm also guilty of, or I'm part of a collaboration where I was going around giving talks saying things like space-time is entanglement. But a lot of what we do at best is, and this is not entirely true, other people can defend JT gravity, but a lot of what we do is we look at a Euclidean path integral, and there we pick out smooth geometries as saddle points. But if I think back to when I was a graduate student and the chair was teaching me string theory, you know, we said things like space-time is a condensate of closed strings. You know, this was dramatically, or more dramatically, evolved with the, I think, well, I wrote down, it was Gary Horwitz, Joe Licken, Ryan Rome, Andy Strominger, and the cubic string action, you know, where they, okay, I'll bring it back to my session. I was inspired to this question because of Janet's talk, where she gave us a picture of holography, but the space-time itself was a very granular picture where you were gluing blobs together. And I know that's a perspective that is, well, appealing to some of my colleagues at Perimeter, and I was just fascinated to see it come up at a
One of the hardest parts of
string
what is space-time, of course, is time.
That was one of my other questions. What is time?
And you just ran out of it.
Okay. I was just setting an example for my colleagues here.
Okay, I just want to highlight one problem that I find very interesting right now, and that's the problem of pure gravity in 3 dimensions. So this, of course, is a pretty old problem. So why right now? Well, the reason is that it's not fully solved, but it's an area where there's been really rapid progress, I think, in the last few years. And it may be, I don't know, but it may be that there's a solution now of this problem that's within reach. There's a lot of evidence for the idea that pure gravity in 3 dimensions is dual to an ensemble of CFTs with large central charge. This comes from doing calculations in the bulk and comparing to conformal bootstrap calculations and random matrix theory predictions. But for a full solution, we should be able to calculate all the contributions from the on-shell topologies in bulk, calculate all the contributions from the off-shell topologies in the bulk. We should be able to do the sum. That might be the hard part, I don't know. And to have some structure analogous to random matrix theory in the boundary, where you can produce these from a CFT point of view. So we have partial versions, partial understanding and examples of all of those. We have lots of examples where things work, but not a systematic answer to any of those 4 parts of the problem. There are lots of interesting ideas in this direction that we've heard about at this conference, both in the previous strings where we heard about random tensors, and this week from Janet, I was also inspired by this work of the announcement of Eric Perlmutter on the solution of the Hellerman bound. You know, if we can bootstrap the lightest black hole, then that really gives some hope that this problem of incorporating black holes into the bootstrap might now be solvable, maybe using the techniques that he told us about. So that's a problem that I hope to hear more about soon. Yeah.
Okay. Juan?
Okay, the session I was chair for had to do with the sitter and models for the sitter. I guess a question, it's an old question, is what's the sitter entropy? And well, there are various developments. We don't know the answer, I think, whether de Sitter entropy, I guess in this session, the idea probably was that the de Sitter entropy is the entropy of some dual quantum mechanical theory that's describing de Sitter. But another option you could imagine is that maybe you should put an observer in de Sitter, and the entropy then will be limited by the degrees of freedom of this observer. You could say, well, the global de Sitter space is just a unique state. There should be zero. So you have all these various options, and we don't know exactly what the right option is. And you could also think that perhaps this entropy has to do with all the possible alpha states that you could have for de Sitter. But I guess it would be very important for understanding, of course, de Sitter space.
Okay.
Okay, I just had my session, so I didn't have time to be inspired by it. So I'll ask a more general question. So, something that's been bothering me more and more over the last few years is when we think, for example, about the black hole interior. So we have stories we tell, islands, the path integral, non-isometric codes. But as far as I can tell, to really interpret the calculations we can do in terms of the interior, we have to make assumptions beyond just, the axioms of conformal field theory. We have to put in some additional input. So in some sense, ADS is not quite equal to CFT. It needs a little more in there. And that's most extreme in the case of the closed universe, where the Hilbert space is one-dimensional, so it seems like the CFT is nothing, and yet you still would like to have some theory or way of doing calculations. And so I would like to think that the thing we're missing is string theory. We're missing the bulk theory of quantum gravity that knows that ADS4 times S7 and ADS7 times S4 are really part of the same theory. And if we understood that, maybe it would give us this extra input to tell us what's going on, say, in the black hole interior without additional assumptions. I hope.
Yeah.
Yeah, I'll ask 3 brief questions related to the 3 presentations in my session. So one was by Eric Perlmutter on the L function, which was a very nice original talk. L functions were originally introduced as a generating functional to count points on algebraic varieties over finite fields. And I wonder whether there's a connection between this machinery and the general feeling that certain things in string theory should be finite, as was also expressed in the talk by Thomas Grimm on the tameness conjecture. So maybe there's a new role for number theory and string theory. Sometimes we see some new math coming up, and maybe this is an interesting moment in time for number theory. The second talk was by Luca Iliesiu, who showed that with gravitational techniques, one could prove the factorization of the Hilbert space in the two-sided black hole. For me, this is an illustration of the fact that although gravity is a coarse-grained theory, it knows that it is coarse-graining over microscopically well-defined objects. But I'm wondering whether somehow gravity, which is a very extremal theory in many ways, it saturates the chaos bound, whether it has in some annoying way been optimized to make its quantum aspects maximally inaccessible to low-energy observers. Which seems to be some conclusion you could draw from these computations, and maybe it's interesting to think about that. And the third question was on JT de Sitter, that reminded me of a long history of doing de Sitter by putting eyes in anti-de Sitter and putting eyes all over the place. And this came up in some other talks as well. And if you put eyes all over the place, you might get the right answers, but the interpretation might be very confusing, like you might get a microscopic model with a negative spectrum density and so on. So my question there would be, what's actually the right contour to do semi-classical de Sitter computations? I find it very confusing. I saw many weird signatures in many seminars. So what's the right contour to do even semi-classical de Sitter computations?
Okay, so my session was on operator algebra methods for quantum gravity. And I have the following question. So operator algebra methods are useful for studying locality, especially in quantum field theory. So you might expect they're useful for understanding the emergence of locality in ADS-CFT. However, in 2 of the talks on my session, there was a puzzle that I don't think was really discussed, which is Hong and Nima defined some local subalgebras on the horizon. And this seemed to apply even in string theory, so finite 't Hooft coupling. So I would have expected to see some kind of violations of locality in this setting. So I find this puzzling. Maybe others don't, but so I have some, there's some speculation about the resolution, which is those algebras they defined were more like a causal wedge. And this is not really stable to 1/n corrections, so things that you heard about from Edward on the cross product. So it's natural to look at entanglement wedges, and so I think there's a challenge there to understand how locality emerges, including stringy effects using entanglement wedges. But then this begs the question of what should we do in a closed universe? So operator algebra methods have also been useful there, so maybe they should be useful in understanding how locality emerges in that setting.
Okay, we used up about half the time. I suggest that there were a lot of interesting questions or comments. Let's let you guys comment on each other's comments. For example, what is space-time? Well, what would an answer look like? Let's say, take a closed universe to be simple.
Well, what I thought was interesting was that there was something, to me, a very different perspective being presented for a string theory conference.
Yes.
It's certainly at the beginnings of a program, but I just thought it was a very interesting set of ideas, and that perhaps some of my colleagues have learned lessons that we can import to that program. But let me ask a question. Alejandra commented on this, that a topic that I heard about every day at the conference, all 5 days, it was de Sitter space. But one of the things that was striking to me is how different each of those talks was. Right. And so I'll pick on Juan. Do you think we're converging on an understanding there, or do you think it's still an open book?
I think it's still a kind of Wild West. So it's an unexplored, somewhat we're exploring various ideas, but there isn't a clear. But let me contrast this with the black hole case. In the case of the black hole, there was this hypothesis that the black hole was described by a quantum system. And this was a hypothesis that, already contained somewhat in the work of Bekenstein and so on. And it was guiding the developments for many years. We don't have a similar hypothesis for de Sitter, which...
Well, there are many.
What?
I thought there were a bunch of different hypotheses. There are people...
We haven't converged. That hypothesis of the black hole is something that most people in our community accepted and understood, but we don't have a similar story for de Sitter. That is consistent with all the facts that we know about de Sitter. So some of the proposals are not consistent with some of the facts.
Do you think we're getting closer? It is remarkable in this conference how much time, how many different aspects of de Sitter space were discussed.
Well, I guess I was picking out this very fundamental thing, but I think it's confusing in many ways, and especially how we should apply de Sitter to cosmology. Should we think, should we think about the Hartle-Hawking wave function? Should we not think about it? How important is the landscape? The fact that de Sitter is not absolutely stable. That hasn't figured in the talks in this conference, but that's probably something important in the context of string theory.
Daniel, looks like you had a...
Yeah, well, of course I don't understand de Sitter either, but one thing that may be causing trouble for us is that, as far as we can tell, at least within string theory, de Sitter is probably metastable at best. And so, it seems hard to have a fundamental exact theory of something that is, fleeting and only there for the moment.
Metastable because of the landscape?
Yeah, because of the landscape, yeah. And so then to talk about it non-perturbatively precisely, you might have to talk about the whole landscape.
Metastable vacuum often end up in some place.
Yeah, but they're all talking to each other, and so some of the hard questions in de Sitter, it seems relevant that it's part of this broader. At least if we still we can say we don't believe in string theory anymore, but we're at the strings conference, so let's believe in it for now. And then, yeah, it seems the de Sitter vacua, they come from somewhere, they go from somewhere. There's this whole dynamical process going on. And it seems a bit much to hope for a theory where you can compute exactly precise things just in the de Sitter without having to know about the rest of that. And that may be why we're having trouble coming up with such a thing. I mean, I may be wrong, I don't know. But
I find it also interesting that if it's dual to a quantum mechanical system, then it would seem that that quantum mechanical system does not necessarily have a Hamiltonian, because there is no Hamiltonian. So maybe it is just dual to a Hilbert space with an inner product, and maybe with some operators on that Hilbert space. But maybe that's even too much to ask for. Maybe it's not even a quantum system to begin with, and quantum mechanics emerges somehow. But definitely it seems hard to believe that it's dual to a system with a Hamiltonian.
Well, most of the discussions require introducing an observer, which has a Hilbert space by definition.
Yeah, but is that a cartoon approximation to something? Or?
Right.
Well, a question there, I mean, I think it was Lenny already mentioned this, that when he thinks of the observer in de Sitter space, it's a fleeting, not the space, but the observer is. And so it would be interesting to understand, what is the experience of that observer who only lasts for a finite amount of time. But I was also encouraged by all the work on, von Neumann algebras. And I have a sense, I'm not an expert, and so I'm asking Tom, I have a sense that we're almost ready, or that's a question that we can, in the near future, answer. We've talked about observers that exist for an infinite amount of time, but thinking about observers who exist for a finite amount of time, I don't know.
Yeah, I think that's reasonable. I think it may be only an approximate notion, so that's tricky with operator algebras. Yeah.
I'd like to emphasize what Jan said, which is, I mean, my interpretation of that is indeed that we need to understand emergent quantum mechanics. It seems strange to have space-time be emergent and not have quantum mechanics be emergent. And so somehow, I would like to think that quantum mechanics emerges in the limit of an infinitely big and long-lived observer, and when they're finite and mortal, need something else, probably something approximate.
Okay, I refrain from commenting, but we're 2 minutes left. Does anyone want to make an important prediction, either about what theory will look like in strings 26, which will happen in X, or anything, or even better, about predictions?
I'll predict closer connections between what we're discussing here and microscopic string theory. Maybe it's a hopeful prediction along the lines of what Daniel was saying, but I think that's one of the things that we really need is to connect back to where it came from.
Yeah, and hopefully the technology of microscopic string theory has expanded dramatically. It was very impressive. Any other predictions? Daniel predicts that after 100 years, quantum mechanics will disappear in some way. We'll hold you to that. Any other predictions?
Well, it's related to the previous one, but it from bit. So
Say it again?
It from bit, what
It
Wheeler
from-
originally said, that not from qubit, from bit. So
Yeah, got
qubits
it.
will come from bits.
Okay, I predict you'll all be back in the audience in 1 minute. So. Great. Well, I think we're off to a good start. That was really fascinating. Second panel, you all know who you are. Renata, Shiraz, Niels, Yang-Hui, Cumrun, and Anastasia. Okay, again, remember the rules? 1 minute, approximately. Comment, question, prediction, anything? And we'll start with Renata.
So the discussion which I want to start,
Close to your mouth, that's it.
is it okay? Is on cosmology, because this seems to be the only place where we can expect future important data. And there will be many different experiments. However, the ones which may affect fundamental physics, which I want to discuss quickly, are when they try to detect primordial gravitational waves from inflation. And in Ed Copeland's talk, you can see one slide from LightBird. Although there are experiments going on now, like CMBS-4, soon we'll have Simon's Observatory and other experiments which are trying to detect primordial gravitational waves and tell us what is the value of R, ratio of tensor to scalar perturbation, which now we know is, the bound is 10 to the minus 2. So the satellite mission, LightBird, will try to go one order below to 10 to the minus 3. And there are, at present, there are 7 discrete targets. And they have to do with alpha attractor models. And there are 2 interesting degenerative cases. For alpha equals 2, there is also a fiber inflation model, which is string theoretical model. And the predictions are exactly the same as for alpha equals 2. Then alpha equals 1,
This is
I am
not
finishing,
a lecture.
is degenerate with Higgs and Stravinsky inflation. Thank you.
Thank you. Anastasia.
Okay, I just would like to say a few words about amplitudes. So in the past few decades, we've been discovering amazing structures in scattering amplitudes. The success of this amplitudes program rests on 2 pillars. So on one hand, you would like to explore the beautiful structures that are there, but on the other hand, we would like to exploit these structures and derive some explicit results and new calculations that are useful outside our field. So outside our field is a key word here. Song Stock described one of those constructions. So he told you a little bit about surfaceahedra for trace phi cube theory, which captures all loop, all 1 over n amplitudes in any dimensions. And you can even get real Yang-Mills theory and nonlinear sigma model from that. So we've been discovering more and more of these remarkable algebraic and combinatoric and geometrical structures over the years. So I think what is important here is to find an explanation of why there are these remarkable geometries underlying scattering amplitudes. It's important to also understand how general the story is and what are some new things that we can learn from fundamental physics from these constructions. So that's my comment.
A comment on your comment just briefly. Isn't it, at first approximation, just string theory? In a sense that all of these theories that easily emerge from the surfaceology are just limits of string
That's right.
theory.
So a lot of these
there
ideas
might be a lot more.
Yeah, I think there's definitely more, and we're just at the tip of the iceberg,
Right.
and there's a lot more. It's for different theories, even for cosmological correlators, et cetera, et cetera. So it's a huge field, and there's a lot more to learn and discover.
Okay.
Great, thank you. So let me begin by echoing David's very invigorating words that this field, one of the greatest things about this community of string theory is how diverse it is. This is a field that works everything from supersymmetry to L functions to number theory to algebraic geometry to representation theory. And one thing I've noticed is that this is reflected by the fact that there have been spin-off annual series from this series of strings. The string math, string pheno. And so my session represents the latest comer to this spin-off session, which started in 2017, which is string data. And this is inevitable because we've entered the age of AI. Yeah. And in my panel, so Vishnu and Bruno gave nice talks about how machine learning can obviously help us with solving problems because we have a lot of platonic data. And Jim Halverson gives the feedback direction to how we can advance research in AI. But there is one more thing that I would like to see for the future, which is AI guided and AI inspired discovery. There is a project led by Terence Tao and Tim Gowers called Frontier Math, which is a challenge to epoch math and to see the kind of problems that we can let machines and AI help us discover to derivations and proofs. So I would very much like to see our community feeding problems to that particular challenge.
Do you think in 10 years we should reserve a talk by AI? ChatGPT. Okay. Shiraz?
Okay. My panel was a bootstrap panel, and there are two bootstrap questions that have been intensively discussed. There's the CFT bootstrap and the S-matrix bootstrap. Now, the CFT bootstrap sounds like a really great program, right? Because fixed points of the renormalization group are discrete, so you're looking for discrete structures in the CFT bootstrap. The S-matrix bootstrap sounds, at first sight, less discrete, because you could take a particle, you could change its mass, you could add some heavy stuff. Clearly, S-matrices in quantum field theory are continuous structures. Now, there's seeming contradiction at first sight, because ADS-CFT appears to relate the CFT bootstrap, namely finding CFTs, to something like the S-matrix bootstrap, namely finding a bulk theory, where the calculation of bulk of the CFT correlator is very much like calculating an S-matrix. And the resolution of this is sort of clear. It seems to be that S-matrices and theories of gravity are not continuous, but are discrete. This is, of course, jives really well with what we've always learned about string theory. It's not easy to move it around. Okay? So my first question is, how do you make this precise? How do you see that when you're in the bulk and you're doing bottom-up ADS-CFT, you take a particle, you change its mass a little bit? That's not allowed. That violates some of the axioms of the CFT, apart from, moving around the tight structure of string theory. Okay, and once you solve that, or maybe before you solve that, the second question is, let's look at this the uniqueness of the S-matrix. Seems clearest for classical S-matrices with gravity. As far as I can tell, the only consistent classical S-matrices with gravity in flat space that we know of, the Einstein S-matrix, the type 2 S-matrix, and the heterotic S-matrix. Maybe we'll find a couple more, but it seems like a really good target for the bootstrap. Prove that for classical, many S-matrices with only poles, no cuts, involving the graviton, these are the only consistent flat space S-matrices. Maybe in the course of this proof you'll find a few more. But it's pretty clear, I think it's going to be discrete. Find it. I think these are great problems.
Yeah. Isn't that what they're trying to do? Isn't that exactly what they're trying to do?
Well, this is a target for the S-matrix bootstrap.
Right.
See,
well, a target coming from ADS.
The first part was coming from ADS. The second part was just in flat space. A lot of actually what people do is study quantum theories. Quantum S-matrices. S-matrices involving cuts. That's a very hard problem. The classic, and we know there are many solutions to that problem because every compactification of string theory gives us a new answer to that problem. But different Calabi-Yaos give us the same classical S-matrix. So there's a much easier and cleaner problem that I think one should focus on, namely the classical.
Niels.
Thanks. Yes, I chaired the session where the common theme was flat space holography. In particular, we heard a talk by Daniel Grumiller advocating or explaining sort of the basis of Carolian approach, which is a codimension one type of holography with Carolian, or rather BMS field theories living on the boundary. Sort of a complementary approach is the celestial approach has had a longer history and has been studied more. So sort of an obvious bottom-up question is, and especially since Carolian field theories, or rather conformal Carolian theories, have been relatively not studied. What are some general properties, in particular of Carolian theories in 2+1 dimensions with BMS4 symmetries? What are sort of general properties that such theories should have to describe flat space holography? And in particular, how do such theories relate to the sort of actions of the type that Anna Maria presented that come from the celestial approach? Is there time for, that's a top-down, it's time for bottom-up? I can come to the bottom-up later.
Okay.
Yes, the session I chaired was related to string landscape, and also related to that was the theme that we heard also in talk by Thomas, and also a comment that Shiraz made. Running through all this seems to be this notion of finiteness, that we only have a finite number of string vacuum. This finiteness is strange. It's not a principle yet of quantum gravity, but it should be promoted to one. There was also a poster, in the poster session, there was a poster also explaining that dualities of string theory, which is one of the fundamental things we have learned in string theory, also is related to finiteness. And they all get related to finiteness of quantum gravity amplitudes when you fully compactify the theory. So the principle of finiteness of quantum gravity amplitudes seems to be an important strand in understanding quantum gravity. On the other hand, looking at the principles we have learned in the context of the Swampland program, we have two rather independent strands emerging. One is issue of holography, which is one of the important principles we all believe in quantum gravity. For example, properties of black hole runs a lot of the aspects of Swampland, like no global symmetries, things like weak gravity conjecture, etc. On the other hand, there's this other one, which is related to dualities and all that, distance conjecture and all that, which gets related to the finiteness principle. How do these two things get connected, or are they connected? Is the finiteness a new principle? Is that somehow related to holography? For example, in the context of ADS CFD, we have ADS 5 times S5 dual to n equals 4 Yang-Mills. Holography is beautiful, but it does not explain why tau is equal to minus 1 over tau. It seems like a completely unrelated, irrelevant question, which cannot be, as we know, in string theory, ignored as one of the important principles. So it seems there are two pillars which are separate. Duality, etc., fall into the line of finiteness. And on the other hand, holography is another important principle which has been one of the main pillars. How do they, is this other pillar exist, this finiteness? And if so, how do these things talk to each other?
By finiteness, you presumably mean countability, right? Because after all, in 10-dimensional space, the string coupling is a continuous parameter, except that it's 1 over n. It has,
So I can be more precise. So finiteness means there are a finite number of vacuum, and in each vacuum there might be there's a moduli space, like coupling constants that Dave is mentioning and so on. Even that is finite morally. Namely, the moduli space of string theory is finite. That's related to dualities, in fact. So duality gets related to that same finiteness. Yeah. So in fact, this principle of finiteness is more broad in the sense that the moduli space of string theory, even if you have massless modes, cannot grow more than Euclidean space in the same dimension. So if it's hyperbolic, it has to have a duality cut it off. Why? Well, that gets related to finiteness of quantum gravity amplitudes when you compactify all space. Why should that finiteness be manifesting dualities in string theory, which is so fundamental? Why is that not a principle of full quantum gravity? In what sense is the principle?
Why is it required?
Why is it required? Why do we want to have, and why is it that you can see it once you compactify all spatial dimensions? Yeah. That's bizarre. We usually don't want to do that. But somehow, when you do that, you begin to see these structures emerging.
Okay. We've, as before, actually covered a bit more than half our time, but we're open for people to comment, question on other comments. There are a lot of fascinating comments. Go ahead, Shiraz.
Yeah, let me start. I wanted to ask Nastya.
They're the speakers.
What?
No.
These new methods about computing amplitudes, do they work for any low-energy Lagrangian, or do they require the Lagrangian to be like that of a UV complete theory in principle? And continuing, is the goal to find some sort of map between these new structures, I don't know, polyhedra, whatever, and Lagrangians modulo field redefinitions? Is that what you envision?
Yeah, I think it's important to understand, explain why there are these structures. So the structure's been found, but yeah, I mean, maybe there's a string theory explanation.
Well, it's not obvious in string theory either.
Yeah.
They very early in string theory, one understood that there was a alpha prime going to zero limit, which recovered field theories, but you only recovered certain field theories. you can easily construct complicated, ugly string theory, and this method only somehow reveal naturally, and still for closed string, open strings so far. Beautiful, lovely.
Yeah, that's
field
what
theories and ones that we use in the standard model and elsewhere.
that's what I was wondering. I was wondering whether this was some sort of. I'm asking you. Okay.
I think so, yes.
Okay. I was wondering whether this
Answer is yes.
Sorry. Answer is yes. Okay.
No, I think there are a lot more to be understood, but they're remarkable structures, and yeah, a lot more.
Renata.
Yeah, I want to add to my comment. So those targets for Lightbird, they are string theory inspired. Therefore, if they indeed discover gravitational waves at some of these targets, it will be a great triumph of string theory. However, we don't know what will happen. So they may discover or not. Anyway, whatever information will come, it will be extremely useful for fundamental physics. Thank you.
For sure. Niels.
I actually also want to more generally echo what Tom Hartman and the rest of the panel said in the previous discussion, like the revival of microscopic string theory. I cannot make a prediction, since famously Niels Bohr said, if it's about predictions, especially the future, is very hard. But I think also the recent developments, sort of the revival of the BFSS model and the IKKT model, Shortu gave a beautiful talk on connection between gravity and field theory on this deformed model. I think, and also, so precisely also there, understanding in the top-down way from string theory, flat space holography, I have high expectations of.
Cumrun, let me ask you, are you willing to predict the future of the cosmological constant?
Well, in the very long term, yes, we're going to decay. That's I think, is a safe bet. I hope we'll find evidence for dynamical nature of it in experiments soon. Maybe it's very soon. And not related to cosmology directly, but other experiments which I hope there might be some results, is potential evidence for extra dimensions, after all, which people are doing experiments clearly even as we speak. So those are very exciting directions for string theory.
That's not a strong prediction, but are there other predictions? Theoretical or experimental? You're obviously going to tell us that number theory is really going to be important.
That's for sure. But I think I think large language models will make very precise predictions of equations that are relevant to string theory.
Really?
I believe in the next couple of years. And this is...
I've been surprised that ChatGPT does not know how to count, but...
better than ChatGPT.
I'm sure. But do teach it to count.
Yeah.
Anastasia.
Shiraz.
Oh, you want to make a prediction?
I have no prediction.
or many. Or too many, yeah. Okay, well then we're exactly on time. And I'll thank the panel. Okay, so we have now our last panel, which includes Ken, Intriligator, Igor. Is Igor still here? Oh, there he is, yes. Hirosi. Rastelli was supposed to be, but left early.
Yeah,
is there?
Only 4 of us.
Only 4 of you?
Yeah.
Okay, and Shlomo. So that all means that you have a minute and a half, which really means 3 minutes.
You're so generous.
So we'll start with Igor.
Okay, very interesting experience. So I'll have two separate comments. One related to the session I chaired, which included a Shock Sense talk on instantons and Shota Kamatsu's talk on IKKT. So Shota's talk was just mentioned by Niels. And I already asked the question after Ashok's talk, he basically talked about maintaining gauge invariance and summing over D instantons, and I asked about the old problem of D0 brane recoil, and apparently this is hopefully can be solved using these types of methods. It also connects with the importance of worldsheet methods of string theory, because at leading order on a disk, the D brane doesn't recoil at all. But we think, of course, that once you sum up all the orders of perturbation theory, it will recoil with energy, which is square root of p squared plus 1 over g string squared. So, but then I want to make another comment, which is partly related to other talks and partly related to what I've been thinking about. So generally, some of the discussion has been about big questions, right? What is space-time, stuff like that. I want to do something a bit opposite to that and propose to think minimally, literally to think about minimal models in 2 dimensions. So the BPZ, Belevin-Polakov homologic of minimal models have been introduced around 41 years ago, and it's a kind of forever young paper, which seems to be again growing in popularity. And at this workshop, at this conference, we had several talks. For example, Hee-Yeon Kim talked about bulk formulation of non-unitary minimal models. So most of these models are non-unitary, and my question is, in the tradition of KITPs, what are non-unitary minimal models? Just to say a word on what I mean, which also connects with what Nastya said. For example, we know that M25 model, so MPQ are non-unitary when P minus Q absolute value is bigger than 1, so most models are non-unitary. The simplest one is M2,5, which describes the Yang-Hui edge singularity of the Ising model in the imaginary B field. And this model, as Michael Fisher proposed years before then, is really I-phi cubed theory. So the phi cube theory, of course, has some instability, but putting in an I, of course, makes it makes the Hamiltonian complex, but makes the path integral presumably convergent. And recently, there has been progress in describing other models in this fashion, these PT symmetric models with I's in the interaction. So there are some concrete questions. Basically, these minimal model, the BPZ paper was a machine for solving exactly an infinite number of field theories, massless field theories, but they didn't tell us what these theories are. And now, 41 years later, we know for the unitary ones through the homological work, and just some very small subset of non-unitary ones. So.
Well, I mean, we heard today physical systems which are described, whose critical points are described by non-unitary systems. But
exactly,
those are
yeah.
Euclidean field theories, if you want.
Mm-hmm.
But are you suggesting that there's a role for unitary CFTs in Lorentzian signature?
Yeah, the question is, what do they mean in Lorentzian signature? Like, for example, Polyakov suggested this role of non-unitary minimal models for turbulence distributions already.
Yes.
That's sort of one part. Like, other more complicated critical phenomena could be described even in the Euclidean sense. And thanks for bringing up Yu Nakayama's talk. He actually did beautiful work recently on with Tanaka on flows between non-unitary models. He uncovered an infinite set of infinite classes of non-unitary flows, and that I think is going to stimulate activity in the near term.
Sounds interesting, but in the context of real time, opening the non-unitary box sounds pretty dangerous.
Well, I mean, these Hamiltonians which have like IX cube, it's sort of a fashionable topic anyways, these so-called PT symmetric systems. So open systems in condensed matter physics have these non-Hermitian Hamiltonians, so that could be a home for such theory. Sorry for going over.
Hiroshi.
Okay, thank you. So I think in general, there have been lots of interesting questions about quantum field theory motivated by the gravity. So a couple of people already mentioned the beautiful talk by Eric Perlmutter. But this was originally motivated by the question in ADS3CFT2 about the spectrum of a state in ADS gravity, imposing condition on the upper bound on the lowest dimension, lowest conformal weight. But so relatedly, I'm very fascinated by the question of can we understand the distance between quantum field theory better? So if we have a conformal field theory and if there are two pair of conformal field theories are related by exact imaginary operator, then there is a homological metric. But you can ask, well, can you define distance between two CFTs that are not continuously connected to each other? So natural approach can be that in the case of CFT, to consider conformal interface, and then try to find some quantity that characterizes the interface. So for example, if we have a manifold and if you have 2 points, there are many passes, but then you try to minimize the distance. So similarly, maybe you can try to find some quantity characterizing interface and try to minimize it. And then, so in more generally, I think I'm very interested in understanding. So the reason, one of the reasons I'm interested in this kind of question is that the asymptotic property of conformal manifold can be related to distance conjecture via ADS-CFT, for example. So more generally, I'm very interested in understanding global geometry of conformal manifold or space of quantum field theory. In general, for example, in the case of CFT, how things like central charge are distributed asymptotically. And those questions can also be related to the issue about the finiteness of landscape that Cumrun mentioned. So I think there are lots of interesting things about geometry of space of quantum field theory. When I was a first-year grad student, I read PhD thesis of Dan Friedan. And at that time, it looks totally like abstract nonsense. But now we are in a position where we can say something quite concrete about this type of question.
Shlomo.
Okay, so my question will be related a little bit to Hiroshi's question. So I chaired the session of Hyun Kim, Yiming Chan, and Pedro Vieira, and the common thread of these talks was use of supersymmetry. So in last 20 or 30 years, we have learned a lot about supersymmetric quantum field theories. And often, or it's fashionable to avoid, we are talking about conformal field theories, but we are ashamed of this word field. So we try to find tools, other tools to describe field theories which are not using Lagrangians. So we have discovered a lot of new theories coming from string theories constructions which are not, we don't know how to describe them using vanilla field theories. So a question that I want to pose is whether there are actually really non-Lagrangian field theories. By that I mean theories that we cannot describe by starting with free fields and then doing something to these free fields, taking certain limits that can be going to in the infrared or going some other limits like a large number of fields and so on. So connecting to the question of Hiroshi, whether this space of CFTs in arbitrary dimensions is complete when we look only on field theories, or we need to add something new, okay? Whether there are new theories that we need, new type of constructions which are necessary. Are there really, truly non-Lagrangian conformal field theories? Again, the 2,0 theory is a canonical example of that, but then I would include constructions like deconstruction, where you start in lower dimensions with usual field theory and take certain limits on the number of fields as describing such a theory. So this is my question.
Yeah, so I chaired the session with Clay on generalized symmetries relating solitons and particles, and then also the talks by Shuhang and Tin on lattice theories with anomalies and also Chern-Simons theory. And I guess I've had the feeling, or many people have for a while, that maybe there's some better understanding of field theory where these different things that look like miracles coming from properties of amplitudes or also dualities might be somehow more clear in some other formulation of field theory. And every now and then, string theory gives us some kind of alien technology that it just gives us some new insights, like ADS-CFT gives us a way to calculate in some other regime, or the theory of multiple M5 brains and the 2-0 theory is some kind of alien technology. And I think in the case of the 2-0 theories, there are plenty of things that we know about them, plenty of exact results. We know that they have order n³ degrees of freedom and many other things, but still they seem very mysterious. And so maybe in connection with the lattice talks in my session, maybe it's a good time to go back and look again at something like the matrix, BFSS matrix model or something, and understand some properties of these theories as some kind of testing grounds for better understanding quantum field theory.
Well, and one of the things it's always surprising to me that there's not even any talks on what is M theory. Nobody seems, people in general, I mean, I think these are, the 2-0 theory comes from M theory, and there are probably many other examples that we don't know of yet, but why have we totally given up on trying to understand what is M theory? How do you do real calculations?
I don't know, I was very surprised by the resurgence of IKKT model, and I would like to understand how this can be connected to other insights we have gained, such as BFSS, and is that like, are these related in some chain of duality, or, because I was very fascinated by this model, but compared to some other dualities, ADS-CFT or BFSS, at that time, I felt it lacked some of the motivation. And so I'm very interested in understanding now, given this recent progress, how this can be fit into what we already know. But I have a question to you. So if somebody gives you a quantum field theory, how can you tell whether the theory is non-Lagrangian or not?
This is basically my question.
Okay.
I will know it by constructing a Lagrangian. Like if it's a question.
Yeah, but so it's a negative question, right? So.
Yeah. So for example.
The procedure.
Yes. So that's basically a question. For example, we have different. It somehow the question is related to emergence in the following sense. So we have various abstractly defined CFTs. We know some properties of them. These theories have a certain amount of symmetry, some operators, some supersymmetry. And then we can find different Lagrangians for, in some cases at least, of these theories, which manifest part of these properties, not all of them at once. So is there any fundamental obstruction?
Right, yeah.
Like, there might be a fundamental obstruction that we just did not find yet, and maybe there is a fundamental obstruction to defining these theories using free fields. So
can you define like something like anomaly?
Yes, something like that.
Yeah.
Yeah, I just wanted to say that this is really the same question I was asking, because when you take, say, critical phenomena in 2 dimensions and then dimensionally continue near upper critical dimension, then you get this nearly mean field description, the Ginzburg-Landau type description. So for example, you take M2, 5, the Yang-Hui edge singularity, you push it to 6 minus epsilon dimensions, and it's just I-phi cube theory. And recently we realized, after actually proposal 11 years ago and then additional touches, that M3-8 model probably doesn't say anything to many people. It's Y3 and 8, but it turns out that it also has a description in terms of cubic theory in 6 minus epsilon dimensions, just with 2 fields and again imaginary coupling constants. So the question is, are all these non-unitary minimal models, can they all be pushed to their upper critical dimensions and have this Lagrangian descriptions? So far, very few are known, but that's sort of a specific version of the question.
Also, like you mentioned Hyun's talk, so you cannot avoid these non-unitary theories. They are hiding as sectors of other theories. So
in Euclidean theory.
No, just in general, like non-unitary CFTs, like this chiral algebra story, they are hiding inside unitary theories. So, and understanding them is often very useful. So.
to make a comment.
Oh, good.
Leonardo?
Leonardo Rastelli.
Oh, great. Where is he?
He's on Zoom. We're going to allow him to speak.
Yes, yes.
Yes, please.
Hi, can you hear me?
Yes.
Yes.
Yes, I'm really sorry I had to leave urgently because of family reasons. So my session was about symmetries in condensed matter systems, but I'd like to bring it back to string theory and ask, of course, the notorious question about the fate of global symmetries in a theory of quantum gravity, which we believe there should be none. There are various ways you could ask the question, but one which is particularly sharp is from an abstract S-matrix viewpoint, and the simplest setup would be scatter two stable, possibly massless, but it doesn't matter, complex scalar states, and insist that there is a graviton pole, so there's a finite Newton constant. And then, given the global symmetries are forbidden, we would expect the symmetry to be gauged, and so we should also see a photon pole. So it should somehow follow from the general framework of axiomatic as matrix theory in the presence of gravity that this is the case. And possibly, the kind of dispersive methods that Sasha Shigoyev reviewed could be used to address this question. There is a DS version of the story where you perform the same experiment, and so you rephrase it in terms of a 4-point function of, say, charged under E1 symmetry operators of the compound theory, and if you insist that the compound theory is local, meaning among other things you should have a local stress tensor operator, you should find that the operator of this function contains a current, which is the boundary dual of the gauge field. So there is a version where this is an axiomatic version where this can be proven. It was done by Harlow and Ooguri, where they did it in the framework of algebraic quantum field theory. If you assume the splittability problem of the quantum field theory, can indeed argue that there has to be a current, or in modern language we would say a topological defect operator. But I think in some sense that's assuming a lot. One is already assuming such a strong locality of the boundary theory that the answer follows rather easily from the axiom. So I think it would be very desirable to obtain such a proof from the standard Euclidean axioms of conformal field theory, which would be the analog of the standard of the S-matrix axioms, but perhaps under more control. And once you've done this, which is step 0, you could then try to ask the question of what about violations? By how much is a global symmetry violated in a theory of quantum gravity? Can that be quantified?
Thank you, Leonardo. Hiroshi, do you have some comment on that? He was quoting your theorem, says it's not enough. It was hard to follow. Yeah. Okay, I think we are at the end of our allotted time. We want to leave time for Ahmed to have the final comments, but just before, predictions.
Okay, I don't have prediction, but I have a wish. My wish is for us to understand how to take the flat space limit of ADS-CFT and use that to either prove or falsify some of the swampland conditions. Like, for example, Ifan and I proved some part of distance conjecture in ADS. Can I just straightforwardly take flat space limit and declare victory, for example? Yeah, so that's the kind of wish I have.
Igor.
Yes, I have one pretty safe prediction, which is that since we're faced with non-perturbative, non-supersymmetric field theory, there are these old-age techniques like epsilon expansion, 1/n expansion, but increased importance of numerical methods is unavoidable, really. And for example, lattice Hamiltonian methods, the Kogut-Susskind methods, are now experiencing a big growth in popularity. Possibly quantum computers will eventually help, but in any case, there are powerful algorithms like tensor networks, which are already giving precise results. And the other comment is not a prediction, but a wish to make a prediction, because as I'm approaching kind of late career stage, I really want to predict something that can be measured experimentally, or at least confirmed numerically, right? So that's kind of been in the back of my mind for a few years now, just to, it could be some critical exponent and some weird non-unitary model. I don't care if it's something small, but I just want it.
Yeah, I wish that desire for predictability isn't disappearing from our community. Shlomo.
So I don't have a prediction, but I also have a wish. It's much more less ambitious. So about 15 years ago, there was an a revolution in understanding of n equal 2 supersymmetric quantum field theories following the work of Gaiotto. Suddenly there was an organizing principle and a lot of things followed from it. So I wish for the same revolution for n equal 1 theories. We accumulated a lot of data, and I think we lack understanding of the structure of the space of these theories and various properties they have. There has to be an organizing principle. It's a wish, it's not a prediction.
Ken?
Okay, maybe I'll partially evade the question by saying I really enjoyed the posters of the young people, and you know, I wish I would have seen all of them, but the ones that I saw were just so wonderful. So I think my prediction is that the young people here will do great things, and I'm happy to see our field is in good hands for the future.
Yeah. I think that's a good prediction because it's bound to come true. So thanks to the panel again. And as far as I understand, our job is over, and we turn it over to Ahmed.
Okay, thanks, David, and thanks to all the panelists. I'm going to be very brief. So I thought about doing strings a few years now, and with the push of my seniors, especially David and Hirosi, I went ahead and did it. It was fun. I mean, it was a lot of work, and there were a lot of sort of bumps in the road that nobody here was aware of, but thankfully things worked out. I should say that at the beginning of this, things weren't clear about you know, from where would I secure funding, for what would the venue be, et cetera, et cetera. So what I'm trying to say is, I'm trying to encourage you that even though it's not clear how things will work out, eventually they will, especially with the support of people like David and Hirosi and the other members of the planning committee. I really encourage you to do it. It's worthwhile. And I also encourage you to be it's an opportunity for you to sort of put your mark in sort of in the design of the conference. So here we sort of tried to be as innovative as we can. We had these panels at the end. We had these discussions after the reviews. And I feel like there were many ideas that we didn't go with. And I'm sure that there are many more interesting formats to explore. Finally, I just wanted to thank all of you for coming. It was a real treat to see you all again, especially here. And I look forward to seeing you again in the next Strings Conference in 2026 for sure. All right, thank you.